So, what we did is this thing called numerical integration. And I need, can you be the calculator person for today? Yeah. Do you watch the video?
I do, but I don't remember how to do it.
Okay, you'll be fine. We'll figure it out. Alright, so what we talk about is numerical integration. And to give like a 2-minute recap of what we did for continuity purposes, basically we were interested in certain integrals, and integrals we were interested in. Can you, is the TV on? I think it is. Can you clear all memory and stuff? What we were interested in was this particular integral. It was the integral from 0 to 2 of e to the x squared dx. Okay. And so can we graph that? Can you put that in y1? We graphed this last class, and if you recall, if you pick a nice window and everything, you see that when you plug in 2, you get some number like around 55. And if you plug in 0, you get 1. And so our function looks something kind of like that. Can you zoom in on like a good window? Because we're interested in interval 0, 2. And then, change the window. And we can do this integral exactly, which Michelle is going to do in a second.
Wait,
on
change the x.
Why?
Change the x.
We can. Do you want to get kicked off this job?
Yes.
Fair.
Okay.
So he's making a nice window. I'll wait.
We should make y like.
Sure, but like I said,
Make y
if you
60.
plug in 2, you get e to the
Make
4th.
y 60.
E to the 4th is like 55 or so. So if you make the window like 60, that's going to look much better. That's going to be an accurate picture of this function on this interval. Everybody good? Okay, and then I want to know what this interval is exactly. Can you put that like over your head?
So, yeah.
Then you can do that. Can you just do that, Math 9?
Wait, do you want me to tape the calculator?
Yep. You have to do both.
Oh man.
You got it. 452. All right. The question that we began addressing with about an hour to go in last class, and which we're going to do this entire class, is how does your calculator do this? And we had a couple of different answers to this question. One way is that you could use rectangles. So you could do LRAM and you could do RRAM methods. And we computed that R20 was 19.3139, and there's a whole complicated procedure for doing that. And we computed that L20 is 13.9541. And then we made the following observations about this function on this interval. What observations did we make which are relevant to this problem? Someone who was here or who watched the video, Mariam.
LRAM is bigger because it's increasing?
Yes, this is an increasing function, and since this is an increasing function, using left-hand rectangles are going to be an underestimate, and using right-hand rectangles are going to be an overestimate. Which means if I define I to be the integral from 0 to 2, which is this number that I care about, then I is guaranteed to be somewhere between L20 and R20, at least for this particular function on this particular interval, because the function is increasing on this entire interval. So I know that I is somewhere between 13.9541 and 19.3139. That is, however, a pretty terrible approximation. How can we do better? We had a whole conversation about this. How can we do better? We can either do more rectangles, although that has its own set of problems, which we discussed last class. But yeah, we can try more efficient methods. So we talked about the midpoint rule, and we calculated that this was 16.3622. And then we also, at the very end of class, did this via the trapezoid rule, and we got that it was 16.6339. Okay, and this is about where class ended. Now, what can we say about this function on this interval? How is trapezoid rule going to work? Like, is that, what can we say? Is the function guaranteed to be between those two? Yo.
Is the trapezoid rule gonna like overestimate because the function is concave up?
Yeah, take a look at it, right? The trapezoid rule says estimate the area under the function using trapezoids. Well, if I split this interval up into subintervals, let's use just like about 3 subintervals for the moment, because then it's more obvious the more you do. And now if I draw the trapezoids, then I see, okay, I'm estimating the area under this function using trapezoids. It at least looks like the function is that this is going to be an overestimate. And why is this going to be an overestimate? Peter already said it. Because it's concave up. All right, so and this is just a fact about about concave up functions. Take some concave up function on some interval from a to b, and if we just graph this concave up function, why does the trapezoid rule have to be an overestimate? Well, it just is, right? This is kind of a fact about functions, which we could have proved way back in the third quarter, but didn't actually. What is our definition of concave up? If f is concave up on the interval a b, another way to say that is
All tangent lines are under.
what's up?
All tangent lines are under.
Yeah, all tangent lines lie below the curve. So that's one way of doing it. That all tangent lines lie below f. And another way of saying it is that f prime is increasing. And it's just also true for any concave up function that the tangent line will lie below the curve, but any secant line is going to lie above the curve. So it is the fact that in a concave up function, the secant lines must lie above the curve. This is something you can even prove, that the trapezoid rule is definitely going to be an overestimate. By the way, is this function definitely concave up on this interval? Maybe we should just do that really quick. So if I take this function, e to the x squared, the derivative will be 2x e to the x squared, and the second derivative will be, I guess I got to do this, right?
2e to the x squared plus 2x e to the x squared.
Then another 2x. I think that's right? So
Yeah.
the first times second plus the first times the third and second. Yeah, so this second derivative is 2e to the x squared times 1 plus 2x squared. That is my second derivative, and of course e to the anything is positive, and this is also positive. So I have that f double prime is just positive everywhere, which means that f is concave up. Actually, it's concave up everywhere, not just on this interval, but all I care about is that it's concave up on this interval. And since it's concave up on this interval, I can actually guarantee that my integral is going to be less than 16.6339. All right. And then, of course, if I draw a concave down function, then it's going to be exactly the opposite. Here is a concave down function. If I want to know the area under this curve from A to B, then just by looking at it, we can split it up into subintervals, and we can draw the trapezoid rule picture. And now, if my function is concave up, then the secant lines are going to lie below the curve, and so the trapezoid rule is going to be an underestimate. Everybody cool with that? All right. Next, let's talk about the midpoint rule. So let me redraw this function, and we're going from 0 to 2. Again, it looks something like this. So my function looks something like this. And now I'm going to, in the midpoint rule, I'm going to split this up into subintervals. And the thing I'm going to do on each subinterval is take the value of the function at the midpoint, and I'm going to make a rectangle for that. Okay, any thoughts about this? What does that look like to you? Underestimate, overestimate, neither, not sure? And go on.
It looks sort of like any underestimation that it makes is like made up by any overestimation it makes, sort of. For every box, like when you have two boxes, you have like a little spot that isn't accounted for, but then there's an overestimate, like sort of.
Okay, so he says it just works perfectly. Is that what you're saying?
Sort of. Not
Yeah.
exactly perfectly, but close enough.
Not close enough so that we just don't care? Okay, but the whole point of this is we care, right? We care about even like the 10th place or the 100th place or whatever. I mean, it looks, he's saying, I mean, basically he's just marveling at how awesome the midpoint rule is in general, which is at least if you have a nice increasing function like this, then yeah, of course, you miss some, you grab some, you miss some, you grab some, etc., etc. And it looks kind of pretty good. It's basically, that's pretty much all I want to say. But I want something more than just, is it about right? I want to know whether it's an overestimate or an underestimate, or maybe I can't tell. Yeah, Eric.
I think it's an underestimate
Why?
because like I think it looks best with the last one. So when you have the like you kind of I split it into like two triangles kind of. Like so you have the triangle that's not being filled and the triangle that's where the rectangle
So
is
like these
over.
two things,
Yeah.
right? Actually, neither of which are triangles. They're
Oh yeah, well,
triangle-ish.
like triangle-ish. And
So
the
you have
thing
these
is,
two triangle-ish shapes. Everyone just mentally just look at it. I mean, does it look about right? I don't know, which one of these looks bigger, this one or this one? Of course, my picture's kind of crappy, but yeah, I think this is bigger, right? Yeah.
because the width is the same, but the height is different.
Width is the
Because it
same, but the
increases,
height
it's
is
increasing.
different.
Yeah,
Alexandra.
the slope of the original graph is like increasing.
Yeah.
Height is increasing.
Yeah, and okay, it's increasing, but in fact, yeah, so the sort of the deep thing that's going on here, right, this function is concave up. This picture works because this function is concave up. And since it's concave up, it means that the derivative is increasing. Well, since the derivative is increasing, what that means is that the rate at which the function is getting bigger is getting bigger. Right? If the rate, what kinds of functions does the midpoint rule work perfectly on?
Lines.
Yeah, lines, right? If you just make a function that's just actually perfectly linear, take a linear function. Well, then the midpoint rule will work perfectly. Why is that? Because if you have a linear function and now you split up into, for example, 3 subintervals, then this is just like perfectly. Because it's linear, I don't know how to phrase this, but because it's linear, now those like actually are triangles, and in fact they're all congruent triangles. Is everybody with me? Okay, so one thing, that's something to appreciate about the midpoint rule, which is that it estimates linear functions perfectly. Okay, so to the extent that this is not linear, anyone, it's not going to be perfect, all right? And how is it not perfect? Well, I think Alexandra was the one that said the key insight, and I think Michelle kind of mumbled it, which is that, yeah, since the function is concave up and the derivative is increasing, the rate at which the function is getting bigger is getting bigger. Which means that the function is going to get more bigger on the right half of each subinterval than it is going to be on the left half. Earlier today during 4th period, we made an example called like babysitting. It was a babysitting example. It was like this. Because what does the midpoint rule do? The midpoint rule basically just kind of checks in on the function at the midpoint of the subinterval. So it's kind of like what you are essentially trying to do when you apply the midpoint rule is you're trying to estimate everything you need to know about the function based on its behavior at the midpoints. So it would be like if you were babysitting some kids for like 4 or 5 hours and you just decided to check in on them once per hour at the half-hour mark. So like they're like a couple of very small children playing with like knives or whatever, but you were just in the other room watching TV, and then like at 7:30 you would just like pop in and take a peek. You'd be like, okay, you guys seem okay, and then you would just go back to whatever you're doing, and then every half an hour or every hour at the halfway through the hour you just take a little snapshot of what they're doing. And then you try to pretend that you can assume that you know what they're doing based on what they were doing at that point. Are you with me? And let's think of this as the troublemaking curve. So they're eating lots of sugar. And the more sugar they eat, the more troublemaking they do. So what's going on here is at the beginning, and since this function is concave up, that means the rate at which they're eating sugar is increasing. So they're eating more and more and more sugar faster and faster, causing more and more trouble. So if you look in on them at the halfway point of the hour and try to estimate how much trouble they've gotten into over that hour, you're going to be off, right? Because the constantly eating more and more candy, getting more and more troublemaking, and then therefore the amount of trouble they're going to cause over the second half of the hour is going to be greater than the amount of trouble they cause over the first half of the hour. Does that make sense? And looking at the midpoints, therefore, not going to be good. Okay, there is even another way to do this, which involves drawing the tangent line. So if I construct the tangent line to these functions on these subintervals, so draw this tangent line, draw this tangent line, and draw this tangent line. This picture is kind of hard to see. In fact, perhaps it's best to just redraw a picture with a single subinterval, just kind of blown up. So here's some subinterval. So let's just call this from xi minus 1 to xi. And let's take a concave up function. And if I have this concave up function, then I'm going to, when I do the midpoint rule, I go to the midpoint and I pretend that my function is doing this. And I take this blue area and I hope that that's a pretty accurate estimate. And of course we see here, now it's even more clear, right? The more you zoom in, the fewer subintervals you have. It's pretty obvious that this is going to be an underestimate, right? But now, an actual proof that this is an underestimate is construct the tangent line to the curve at the midpoint. If I do that, that produces a trapezoid. And what is the area of this trapezoid? Say something about the area of that red trapezoid. Okay, my picture is kind of crappy, but it is in fact exactly equal to the area of the blue rectangle, right? Because now that this is the line, like these two triangles are congruent. I could even like prove this to you, right? I mean, this is, these two are like congruent segments, right? Because it's like a midpoint. And then these are like, angles are congruent or whatever. And then because this is parallel, like so are alternate interior angles congruent. Follow? So therefore these two triangles are congruent by like, AIS or some crap like that. And therefore this triangle outside the red trapezoid is the same as this triangle missing. So actually, every midpoint rule is really just like a trapezoid rule in disguise. And what can we say about the relationship between this red trapezoid and the true area under the curve? It's definitely an underestimate. That's because of our definition of concave up. The definition of concave up, tangent lines lie below the curve. So since tangent lines lie below the curve, the tangent line function will be strictly less than the function except at the midpoint. And so this red area must be less than the true area, and the red area is equal to the blue area. Okay, these are key observations. When you have increasing functions, LRAM will be an underestimate, RRAM will be an overestimate, and then vice versa for the switch. If you have a concave up function, then the trapezoid rule will be an overestimate, and the midpoint rule will be an underestimate, and it's reversed the other way. Alright, so now I can confidently conclude, based on all these numbers that we did last class, that since this function is concave up, and I've demonstrated that, then the true area under the curve must lie somewhere between M20 and T20. And this is a pretty good estimate, actually, because we computed last class that M20 was 16.3622. And now, look at how much better that is than what we get using rectangles. It's like dramatically better, or what we use getting LRAM and RRAM, right? Here we narrowed it down to an interval of like 6, which is like terrible. Here we got it down to more or less, plus or minus a couple tenths, without having to do any more work, right? Basically, or a little bit more work, but no more subintervals. Okay, so that's kind of like that's kind of like the conclusion of the first, that's sort of what I hoped to get to last class. All right, the problem is this doesn't totally work all the time. Let's take a new function. Let's take the integral from 0 to 2 of sine of x squared dx. All right. What's the problem with this function? And Eli should be graphing it already in line 1 and making a graph and fixing window. But he also wants to raise his hand, so someone else is going to have to do it for him. Connie, what's wrong with this function?
You can't, like, the antiderivative.
Oh yeah, that's one problem. It doesn't have an antiderivative, and so I can't apply the fundamental theorem of calculus. Why can't I just do all this stuff? You all can type it on your own calculator too. You don't have to wait for that. Okay, bad window. Also bad window. Think about it. It's a sine function, right? So it's like never going to be bigger than 1. Nope, but I still want to go from 0 to 2.
But why? Why
These
minus?
guys, there's a lot of pressure being the man with the calculator. Especially from screaming at you all the time. Yeah, okay, there you go. Beautiful function. So what? It oscillates. Can you say something more specific? Yanni. Yeah, the concavity changes. Just looking at it, at least just by eyeballing it, it appears as if the function is concave up, and then it's like concave down, and then it's concave up. In fact, we can just do this, right? Let's just look at this function. If f(x) is sine of x squared, then okay, we can take the derivative. If you take the derivative, you get sine of x squared back to sine 2x. All right, now I have to take the second derivative. So this is a little bit annoying, but derivative of the first, probably that should be cosine. Hold on a second. Yeah, that's good. Now this is going to be negative sine of x squared times 2x for the first times the second plus the first times the derivative of the second. I think I did that right. So I get something kind of gross. It's going to be like 2 cosine x squared minus 2x squared sine of x squared. I did this on my paper. Yep. Okay. And now I think Eli's doing good things maybe. Can you go back to y equals? You have so many things on the screen.
Yeah, I tried zooming out to see if it would work.
Okay, can you go back to y equals? No, stop. Y equals. Can you deselect y1 and y2 because we don't want to look at them? And that is the function so then can you change the interval still from 0 to 2? Yeah, exactly. That's fine, just hit graph. So he's now graphing the second derivative. And now, yeah, confirmation via technology that the thing is changing concavity. In fact, can you find those points using the 0 command? And while he's doing that, does anyone have an idea, even though this function changes concavity, do you have an idea of a way we could still get an upper bound and a lower bound on this thing? You could split it up. Michelle says split it up. Yeah, this is like divide and conquer, right? The divide and conquer method says split this interval up into subintervals. I think you did something wrong because I know the answer is not 0.76. I don't know what happened. Did you type the wrong function? Minus 4x squared. Negative 4x.
You
Would
have.
that be
X.
squared?
X squared.
It's x squared, 2x squared.
Oh. Okay.
Yeah, it should be a square. I think that's right now, right? Okay, anyway, he's going to do it, but I think I already did this a while ago. And I got that it was concave up on the interval 0, 0.808. Is that what you're getting, Eli? Or he's about to get that. And then it's concave down on the interval 0.808, 1.81. And then it's concave up on the interval 1.812. But this sounds kind of terrible. I could do this. What I have now done is I have partitioned the integral into three other integrals in which its concavity is like constant. And then what I could do, but I really don't want to, is I could compute the integral on the interval 0 to 0.808. Knowing that since it's concave up, I could use the midpoint rule and the trapezoid rule. You guys following this in theory? And you could get an overestimate and an underestimate. And then you could go where it's concave down, compute the midpoint rule and the trapezoid rule, and then the which one's an overestimate and which one's an underestimate would flip. And then you would do this one, you'd have these three inequalities, and then you'd have to add them all up or something, and you'd get a bound on the interval. Okay, that sounds terrible to me. It's really annoying, it's not easy to do, so it would be nice to have to not do this. Alright, so what we need is, though these conversations we had here on this backboard are important for understanding how the midpoint rule and the trapezoid rule, how concavity affects that, this is, in practice, if you have a function where the concavity is changing, this doesn't seem like a good idea. So what I want to do is I want to just do this once. I want to just use one of these rules, and I want to just know how much I'm off by. Alright, now this is kind of tricky, right? Because you can't. So let's take a new function, or let's take the same function. Let's take some function. One second. Let's take some function, and we want to figure out the area under that function. And I want to know by how much I'm going to be off by. And this is important, because when we are estimating, we're trying to estimate these intervals. Doing an integral and getting a number is worthless if I don't know how much I'm off by. So for example, Stein talks about this a lot in statistics class. You can say all kinds of stupid things that are technically correct. For example, in my savings account right now, I have approximately $1 million. True or false?
False. False. True. Maybe.
How approximate?
Yeah, how approximate? It's approximate to around plus or minus $1 million. Okay? So I'm not wrong. I do have approximately $1 million. I am just saying that I'm reporting my bank balance, with an error of plus or minus $1 million. And you can just keep playing these kind of stupid rules, right? I weigh approximately 15 pounds. Plus or minus, 180 pounds. Or something like that, right? An approximation in and of itself is useless. If you tell me that this integral is about 16.6339, you have given me no information. I have no idea what I'm supposed to do with that number. Okay, it's approximately 16, but what are you off by? Are you off by a tenth? Are you off by 10? Are you off by 100? Right? A single approximation by itself is worth nothing. What I need to be able to do is I need to be able to compute these integrals, and I need to be able to tell you by how much I'm off by. Alright, now, the thing is, you can't tell me exactly by how much I'm off by, because if you told me exactly by how much you're off by, then you would basically just be telling me what the answer is, and that's what I don't know. So what we have to do is we have to figure out some way of putting a cap on the error. Alright, so what happens, where does the error come from? Let's take LRAM, for example. Looking at LRAM, what kinds of functions are going to make LRAM be inaccurate? This is kind of a vague question, but it's
Concave.
intentionally vague. What kinds of functions are going to make LRAM be inaccurate?
Wait.
Yeah, anyone?
Not straight lines.
Not straight lines.
Not straight lines. What do you mean by straight lines?
Like anything that's curvy.
Actually, wait.
Curvy.
Straight lines would do it too, wouldn't it?
Thomas, what's up?
You.
I do. Okay, curvy. Anyone else? Eli.
Something that's both concave up and down.
Something that's both concave up and down, but sometimes I might just balance it out, actually. Let's think of picture in your brain for a second. What is the function which will mess up LRAM the most? Yeah, Peter Ho.
Positive slope.
Positive slope.
Yeah.
And you go on.
A straight line with a positive slope messes it up pretty bad.
Yeah, right. So first of all, maybe a simpler question. what kinds of function will make RRAM be perfect?
A
When is
horizontal
RRAM
line.
perfect? Or when is LRAM perfect? There's only one kind of function for which LRAM is going to be perfect.
A horizontal line.
Yeah, constant functions, right? If you give me a constant function on some interval,
That's one.
and I graph this, the LRAM is going to be perfect on this interval because I'm going to split it up into subintervals. I'm going to pretend that what's happening is what happens at the left endpoint, and I'm going to actually get it to be perfect. All right, what makes LRAM what? Is something you're saying important?
What messes it up the most?
Yes, what messes up the most?
Vertical line.
Okay, that's not a function. So what is going to mess up LRAM the most? Functions with big slopes, basically. Right?
Almost.
If you give me, like, let's draw a function like this. So it actually doesn't matter if it's curvy. I don't think concavity is relevant either. Just give me some kind of function that looks like this. Here, all right, LRAM is going to be off, but it's going to be off by, maybe not so much. So that's kind of bad, but not too bad. But here's an example of pretty terrible. I can make this be terrible by just having this be like a really big slope, right? Intuitively speaking, if I have a big slope,